talk number 2. Thank you all for coming. I appreciate it. Today, we're going to talk about something we didn't talk about last time. We're going to talk about bathymetry. And what bathymetry is, I know that's a big word. What that means is bumps on the bottom of the ocean. And we're going to see if we can model that. But we got a whole bunch of introduction to do. So this is me. I teach at Seattle University, but this semester I'm on sabbatical working with Panos here. And we're studying some of the things we're going to talk about today. This semester, I'm at EMAS, which is like a 5-minute walk from here, and I'm having a good time. Last time I told you I was going to try to eat 1,000 tacos while I'm here. I've eaten like 120. So I've got a long ways to go in the next 4 months. So many thanks to Digapa and Panos for supporting my time and stay here. It made this trip possible. So in a month, or in like 6 weeks, in the middle of October, I'm going to talk about modelos de ondas en mares profundos. And there's a small chance, or maybe a medium chance, that voy a charla en español. Es una meta, pero no puedo hablar muy bien, y no, I don't want to kill you and make you suffer. But I want the practice. So por favor, tell your friends about this talk so that they can come and learn about waves in the deep ocean. So, in case you weren't here last time we talked about waves on shallow water, but we only talked about waves on shallow water with a horizontal seafloor. We ignored bathymetry. What did we talk about? We talked about tsunamis, some models, some dispersion relationships. We did experiments. And then we actually compared with some real data, not from just the lab, but also from the ocean. I'm going to do a little bit of overlap, maybe 10% overlap today. So if you remember something from before, that'll be good. What are we going to talk about today? We're going to talk about the effects of bathymetry. So here's a little outline of what we're going to do. We're going to start by talking about mathematical models. What are the equations we want to use? Those equations are too hard. So we're going to try to simplify the problem, and we're going to try to narrow it down to a very simple topic so that we only have one thing to examine. Because if you have many things to examine that are all changing at the same time, it's too hard. Then we're going to talk about solving the simplified problem. We're going to talk about designing lab experiments. I'm a mathematician. I'm not an experimentalist, so give me some leeway here. But I've worked a lot with experimentalists, and I've learned a lot from them, so we'll talk about things that can go wrong. And then at the end, we're going to talk about comparisons. We're going to start with comparisons with a flat seafloor, and then also with a non-flat seafloor. So we're going to have some bumps in the bottom of our ocean, and we're going to see how that does. As I said at the outset, I'm an applied mathematician. So I really like this talk because it does everything I think that applied mathematicians should do. What should applied mathematicians do? They should do a modeling. So you should write down some equations that tell you what's going to happen. Then you should do some asymptotics, because usually the models you have are too complicated. So you need to approximate them, asymptotics or some other approximation. Even then, the equations you end up with are too hard, so you have to do numerics. So you use your computer, you write some code in Python or Julia, whatever your favorite language is, and you find approximate solutions to your equations. Then we do experiments, and then you do some testing. This is what it is to be an applied mathematician. So we're going to walk through all of these steps today. I come from a teaching university, so please interrupt me with questions. Throw a rock at me, just raise your hand. Whatever. And to make things more fun, I'm going to tell at least one lie in this talk. And if you tell me when I tell you the lie, you get this. And I have 2, just in case I tell 2 lies, okay? So let's begin. What do we need to know? We need some equations that tell us what's going to happen to our water waves, okay? What things impact water waves? What do you want our model to include? Let's see how many things we can come up with. I think I have 11 things on the next slide. I'm sorry? Okay, viscosity. Good. That's great. We want to include viscosity. What else? Ah, great. Surface tension. Great. Two things. What else? I'm sorry? Oh, density. Yeah, the density of the water is important, because if we have salt water or if we have fresh water or seawater, it makes a difference. Good. What else? Ah, yeah, humidity, right? Is the water evaporating and things like that? Good. Okay, two more, please. Ah, okay, good, good. The seafloor. That's why we're at this talk today. We want to include the seafloor. Good. Six, last one. Temperature, sure. Temperature could play a role. Let's see. What do I have on my list? How many of the things that you said are on my list? So I said wave speed, so surface tension. I put viscosity on there, temperature, density, seafloor. So I think I got everything that you said. This is what we would really like to have our model include. That's way too hard. Every one of these things makes your PDEs, your partial differential equations, more complicated. So what are we going to do? I love this quote. Everything should be made as simple as possible, but not simpler. So you want to make it easy, but you want to make sure that it's not so easy that you don't learn anything from it. So today, if we said, okay, let's have a horizontal seafloor so there's no bathymetry, we would learn something, but that wouldn't help us answer our question about bathymetry because we want to know how the seafloor is going to impact our waves. So keep an eye on this and think about this quote. So, as we've said a couple of times, we want to study bathymetry. So what are we going to do? We're going to study bathymetry and we're going to ignore almost everything else, which makes us a little sad. But it's the best we can do. Well, it's the best that I can do in 50 minutes. So what am I going to do? I'm going to make some simplifying assumptions in relation to that list of things we had on the board. I'm going to assume that mass is conserved. That's a pretty reasonable thing. Hopefully you've taken enough physics classes that you know mass is conserved. So this means something like there is no evaporation, there is no humidity, so all the water is just a chunk of water. The seafloor is impenetrable and does not move. So that means it's not like sand, because if the seafloor is sand, then the waves or the water could go into the sand and water could come up from the bottom of the sand. That's not happening here. There is no y dimension. I could add the y dimension to everything I'm doing today. I don't want to do that. I'm going to assume that the water is inviscid. That means there's no viscosity. Irrotational, that means there's no, what's the word? Spiraling. Vortices, thank you. And the water is incompressible, so that means the water has constant density. Ocean currents don't play a role, tides don't play a role, surface tension doesn't play a role, wave breaking doesn't play a role. We're ignoring all of those things. There's one important thing I left off of this list. Right now, I've simplified my problem too much. Does anyone know what I left off of my list here that we need to include to accurately model water waves? Please come on, have a chair. Please come on in. Oops. We forgot about gravity, right? If we don't have gravity, the waves are just gonna not do anything. They're not gonna move. Gravity is the restoring force. It's gonna be what causes the waves. So make sure you don't simplify your problem too much or you're not gonna learn anything. Gravity. So here's our system. And we got some waves up here. Z equals 0 is what's happening to the fluid when it's not doing anything. It's just sitting there. Z equals 0 is that. So I think we lost our zoom. Could you? Yeah, it lost internet connection. let's hide these. Oh, there, it's already gone. Okay, gracias. So here's our physical system. Z equals zeros. What happens when the water is doing nothing? And then we have the bathymetry doing something or other. And the only thing that I require is that H naught takes into account the majority of it, and beta here is the bumpy part of the bathymetry. You do some physics, this is what you get. You get a big mess of equations. This first equation right here, tells us that mass is conserved. That's good. That's one of the things we wanted to be true. We wanted mass to be conserved. Here, this equation at the bottom, Z equals minus H naught plus beta, that's the bottom of my ocean. This thing right here tells me that water doesn't go down into the bottom and it doesn't come back up from the bottom, which was another one of the things we required. And then these two other equations, which are both evaluated at the surface, tell us that there's a balance of pressure from the air and the water, and that also that if you're a particle on the surface, you don't fly off into the air. So, okay. Last week or last month when we had this, we talked about the equations with a flat seafloor. What changes? Well, not much changes. The only thing that changes is that beta goes away, that beta goes away, and that beta goes away. So you get this system of equations right here. I should have said this a second ago, but eta is our water depth and phi is our velocity potential. And the velocity potential, if you know what the velocity potential is, you know the velocity of the fluid. So if you compute phi sub x, the partial derivative of phi with respect to x, that tells you how fast your waves are going in the x direction. If you compute phi sub z, that tells you how fast your water is moving in the vertical direction. So it's pretty nice. We know our water depth and we know our velocities. That's what we want to know because we want to figure out what's happening to our water. Okay, yeah, so that's the difference between those two equations with bathymetry and no bathymetry. Those equations are difficult. Why are they difficult? The main reason they're difficult is because I've got a nonlinear term right there, a nonlinear term right there, a nonlinear term right there. And also, the upper boundary of the ocean changes in space and time. So all of that makes it difficult. If you were here last time, you learned about how difficult these were. They're nonlinear. We just said that. Blah, blah. We just said that. How difficult are they? These guys in the Math Clay Institute will give you $1 million if you answer a question. And all you have to do is go to their website and read this and solve it. And then you'll be rich and you can be a mathematician for the rest of your life. So let's start with a simpler problem. Let's start with horizontal seafloors. So this is the system of equations we want to solve. Even though I've set beta equal to 0 and we don't have bathymetry anymore, this is still too hard for me. I'm not very smart. That's too hard. Actually, even if you're really smart, this is really hard. This is the same picture as before, except now we don't have bathymetry. We have a flat seafloor, basically the same. But now we have all these new parameters. We have H, which is the wave height. We have H naught, which is the depth of the water. And we have lambda, which is a wavelength. How long are our waves? Those parameters are going to help us classify the type of equation we want to use. So those are the three variables. Epsilon is a measure of nonlinearity. What you do to get epsilon is you take the wave height and you divide it by the depth and a factor of 2. Delta is the depth divided by the wavelength. And you can derive, using a whole bunch of asymptotics, various equations based on these parameters. So what are we going to do? We're going to assume this. Remember, eta is my surface displacement. and phi is related to my velocities. What I'm going to do is I'm going to put epsilons in there. And remember, if you've taken enough math classes, you know that epsilon is always a small thing, right? So what I'm doing here is I'm assuming my surface displacement is small, and I'm assuming my velocities are small. And then I've got this small term here, and then this term right here is even smaller, because if you have a small thing and you square it, it's even smaller, and then this is a super small thing. We've got all of these small terms. We're going to add them together, and we're going to take these equations, and we put them into here. And then if you do, I don't know, say 5 pages of differential equations. Oh, yeah, I have to tell you this. We already said that we're assuming epsilon is small. You assume that you have long waves in shallow water, which means delta is very small. We're going to assume that epsilon is equal to delta squared because that makes the asymptotics nice. And if you have nice asymptotics, you can smile. And I'm also going to assume unidirectional waves. And a couple of these things are going to kill us later in the talk. So we're going to have to get rid of some of these restrictions later in the talk, but we'll talk about that later. If you do all of this and that 5 pages of differential equations that I told you about, you get this PDE right here. So what did we do? We converted the 4 PDE, the Euler equations, into this equation right here. This equation right here is pretty nice. It's called the KdV equation. Believe it or not, it was derived for the first time in 1898. So this equation is over 100 years old, and people like me are still studying this equation. It's nonlinear because I've got this eta x term there. That's a nonlinear term. These are linear terms. This equation right here tells me what happens to my surface displacement. It tells me what happens to eta. If you want to figure out your velocities, you have to do a little bit more work that I'm not going to talk about today. So, what are the weaknesses of the KdV equation? Well, it's only accurate for long waves. We made that assumption in the asymptotics we did. It's only accurate for small amplitude waves. Remember those epsilons we had in our surface displacement term? That's when that comes into play. It's unidirectional. Horizontal seafloor, no dissipation, no viscosity. And something that's interesting that I want to point out and talk about a little bit is it misses all of the Euler instabilities. What does that mean? Well, we started with the Euler equations, right? That big mess of equations, and we did a whole bunch of stuff to get the simplified KdV equation. If you were an awesome person, you would like your KdV equation to have exactly the same properties as the Euler equations, right? Because if you're trying to approximate something, you want them to be like the same. One of the big differences between the KdV equation and the Euler equations is that the Euler equations have instabilities, while the KdV equation doesn't have instabilities. What does that mean? Well, that's a big deal because let's assume we're in KdV land. So you have some waves and the waves travel. Those waves are going to travel forever and everyone's happy. Nothing ever really happens to them. Even if you perturb them a little bit, they're going to still travel forever and basically keep their same shape. But that doesn't make sense for what we know happens in water. What happens when you have waves in the ocean? If you start with some waves in Euler equations and you send them down, they're going to travel and they're going to keep their form just like normal. However, if you start with those same waves in the Euler equations and you perturb them a little bit, so you stick your finger in the water or you blow on them or you do a little bit, what's going to happen as those waves travel, they're going to break up. They're not going to be exactly the same after a while. That's what happens in water. So the KdV equation doesn't have that property, bumps us out a little bit. So let's try to get rid of some of these restrictions. We have this KdV equation right here. It's only accurate for long waves. Whittam in 1978 said, okay, I know how to solve this problem. This is what you do. You take KdV, these first two terms are KdV, and then you replace those linear terms with that thing right there. And what that thing right there is a convolution. Convolution might seem scary, but I'm going to show you how to deal with it numerically very easily in a few minutes. So it's scary. What is it? Kappa is a convolution with this Fourier multiplier. So it's got a hyperbolic tangent, it's got a k in the bottom. But numerically, that's very easy for us to deal with. So this is the Whittem equation, and the Whittem equation works for long waves. So what did we assume? Well, it's got the same assumptions as KdV, except we removed the restriction that it only works for long waves. Yeah.
Works only for long waves.
Yes.
But how do you compare this long wave with respect to the heat of the body?
Yeah, that's exactly what we do right here. KdV is derived assuming delta is small. So H naught, which is the depth over lambda, which is the wavelength, has to be a small number. So I want lambda to be big. So this is exactly how we define what shallow means. I appreciate the question. Please ask questions. Okay. Okay, so yeah. Well, so we still got some restrictions. It's only supposed to work for small amplitude waves. It's got the same appropriate balance, and it only works for unidirectional waves. So we still have a whole bunch of restrictions. Well, we can still test it. Here's our Whittem equation. What happened? I had this. Oh, yeah. We're doing the same thing again. I'm here for 5 months, right? I'm working with Panos and Gerardo over in the fluids department. And we're studying what happens if you reduce this, if you remove this restriction and you remove this relationship right here. This is a question that Panos asked me a couple of weeks ago. What happens if this doesn't hold? And it turns out that epsilon equals delta squared. All of the experiments that I've compared with so far until today, basically epsilon is equal to delta squared. I just didn't know it. So it's interesting. It's going to be very interesting for me to test what happens if epsilon isn't equal to delta squared. Will these models work? I don't know. So this is a place for a pause. Any questions so far? Please. No? Please.
Let's talk about the order of stabilities. For the way to break, you need to cover the variation in the bottom.
You don't need variation in the bottom for the wave to break.
You break to cover the vertical slab.
Yeah, you don't need that. No. What you need is you need a wave of sufficient height. And if you have a wave of sufficient height, it's going to be unstable, and that instability leads to wave breaking. And the KdV equation doesn't have that. That's exactly right. The Whittem equation does have that, but it doesn't exactly line up with the Euler results. So that's why I didn't want to talk about it. And I'll say more about this in a few minutes. Okay, so we have this equation, right? It's got a whole bunch of problems, but okay, it's a place to start. Can we solve the KdV equation? Yeah, you can solve the KdV equation if you use inverse scattering, which is this thing you learn in graduate school in applied math, if you go to the right university. But an easier way to do it is just to do it numerically. I like numerics, so what we're going to do is we're going to learn how to solve the KdV equation numerically. So here's the KdV equation. What are we going to do? We're going to split the KdV equation into two parts. We're going to split it into its nonlinear part, which is this stuff right here, and then its linear part, which is that stuff right there. And we're going to solve the linear part first, and then we're going to solve the nonlinear part. And then if you do a dance between the linear part and the nonlinear part, and you sort of solve them like this, you get an approximate solution to the KdV equation. Because really what you want to do is you want to solve them both at the same time, but that's too hard. So what do? We split it into the linear part and the nonlinear part, and this thing that I'm describing to you is called operator splitting. So what do? You have to solve the linear equation first. How do you solve the linear equation? Here's the linear equation. I now gave it a number 1. But how do we solve that? Okay, I'll give you a hint. We're going to use Fourier series. Oh, I was only supposed to click once. Sorry. I just showed you the solution. So we make this assumption right here. We assume that our surface displacement is a sum of a whole bunch of Fourier modes, which means e to the ikx's, an infinite number of them. We take number 2 and we substitute it into number 1, and we do a little bit of algebra, like 3 lines of algebra, and we get this differential equation right here. This is an ordinary differential equation here. How do I solve this ordinary differential equation? We don't even need to do it numerically. We can solve this differential equation exactly. This differential equation is like y prime, because it's the derivative, plus a constant times y. Y prime plus a constant times y equals 0. We know how to solve that. We solved it. Separation of variables. So this differential equation, we can solve it exactly using separation of variables. What do? You get this right here when you do your separation of variables. So this is pretty cool. So what did I do? I used Fourier series to come up with an exact solution to the linear problem. I'm ignoring the nonlinear problem for right now, but we've got the linear problem solved. This is it. So how do we do this when we're sitting in front of our computer coding in Python? What do? We take 3 steps. Step number 1, I showed them all at the same time. Step number 1, take an FFT. So you just do FFT data. Easy. Then you take your data and you multiply it by e to that constant times your time step delta t. Then you take an inverse FFT. So nowadays, this is super easy because you just call this FFT because it exists in Python. You call this IFFT because it exists in Python, and you just have to do a little bit of multiplication. When I was a graduate student 250 years ago, I had to write my own FFT because, well, mainly because my advisor thought it would be good. It was a good experience, but it sucks. So this is good. We know how to solve the linear problem. What do we need to do now? Now we need to solve the nonlinear problem, right? We're halfway there. So here's the nonlinear problem. I did it a little bit differently. I wrote it so that it's y prime equals junk. How do we solve this? Well, I'm going to think of this as an ODE. It's clearly not an ODE, right? Because I've got an a to t and an a to x. But I can still think of it as an ODE. How I'm going to think about it as an ODE, I'm thinking about it as an ODE in time. So what do I need to do? I need to know eta. Okay, that's my surface displacement. I know what that is. I need to compute eta x. And you can compute eta x a number of different ways. You could use finite differences if you wanted to. But since we've got these FFTs laying around, I'm going to compute eta x using FFTs. So you take some FFTs, you compute eta x, and now we know everything on this side of the equation. That's pretty nice. We know everything over there. Just use RK4, 4th order Runge-Kutta. That's easy. Hopefully you learned RK4 when you took a course in differential equations. If you haven't, it's the most powerful method for differential equations that are first order and satisfy some criteria. So learn about RK4. So this is great. We now have a solution to the linear part and the nonlinear part. So we do our little dance and we get an approximate solution. We feel good. We know how to solve KdV. What else do we want to do? We also want to solve the Witten equation, right? The Witten equation has the same nonlinear part. So we already know how to numerically solve the nonlinear part because I just showed you how to do it. But we've got this new linear part. So let's deal with this new linear part by Fourier series and separation of variables. It's exactly the same process. We make, use operator splitting. Yeah, here's our Fourier series. This gives us this differential equation right here. This differential equation right here is y prime plus a different constant y. Use separation of variables again. We get eta hat is the initial condition times an e to the delta t stuff. Easy. Exactly the same as KdV. The Woodham equation is a better model, but computationally, it is faster to solve by this much than the KdV equation. Okay, so now we've done all this math. We've got the KdV equation and a numerical solution in our back pocket. We've got the Woodham equation and a numerical solution in our back pocket. We want to test these equations. We want to know how they are. How much money have we need to spend so far? Well, you need a computer. So you go to the library or wherever the computers are here on campus, and you use a computer and you write some code in Python, and you're done. You have an approximate solution. How do you design a lab experiment? This is a lot more difficult. You can't just go to the library and there's not just a whole bunch of lab experiments sitting there for you to do. So what do we want to have in our tank? Well, there's three main components that you need in your tank of water. What do you need? Well, you need ideal measurement devices. You want your ideal measurement device to be accurate, right? Because the data it collects needs to be useful. It needs to collect it quickly so that you have a lot of data. You need to be able to measure wherever you want, right? Because if you're interested in what's going on over by that wall, but your gauge is over here, it doesn't help you so much. Finally, you don't want your measurement device to impact the waves, right? Because if the gauge gets in the way of the waves, that's going to sort of ruin everything. You're going to say, well, the gauge is the reason for that to happen. You don't want that to happen. You need a gizmo that's going to create the waves. We call this a wave maker. So it's a plunger or something that goes like this or something that happens that's going to make the waves. You want it to be very precisely controllable. You want it to span the width of the tank. So you have this tank and you want only one dimension. That's because of that assumption that we've said at the beginning that we're ignoring the y dimension. If you want to include the y dimension, then you can cross out that spans the width of the tank comment. Another comment about the y dimension. And then this has the right shape. Diane Henderson, who's one of the best experimentalists I know, she has a lab at Penn State University. She did an experiment where she had a paddle that went like this, and the waves went this way. Then, instead of using a rectangular paddle, she used a triangular paddle. Did this. The waves were quite different. Then she did this same experiment with an exponential decay on the front face of the paddle, did it again. And then it lines up with the theory that everyone believes. So the shape of the paddle is very important. At least to me, it was more important than I realized. I thought the water would just do the right thing. But you need that exponential decay in order to get what you think is the right solution. Then what do you need? Then you need a tank, right? What do you got to do? Well, you gotta make sure that the walls and the bottom don't cause waves, right? Because you want to just examine the waves that are created by your wave maker. You want it to be isolated from external motions, because if you come up and you hit your wave tank like this, that's going to cause a whole bunch of waves and it's going to cause a whole bunch of noise, and you don't want that. You only want the waves that you want to be there. If there are other waves in there, you're in trouble. You have to have the right dimensions, and you want it to be inexpensive. Diane has 2 tanks in her lab. One of the tanks cost $1.5 million to build, which is ridiculous. But does it fly? No, but it's beautiful and it's 2-dimensional, and she can have this y dimension stuff, and she can do waves of shallow water and waves of deep water. And it's got all these measurement devices that mostly don't impact the waves. And the most expensive part is this right here, is the computers and the systems that control the paddles. Because there are essentially 32 paddles in her tank. One, and they're all 2.5 centimeters wide. You might know why it's 2.5 centimeters wide, and there's a whole bunch of them. And yeah. This is a big deal. What happens if you screw up? If you make a mistake, you just spent $1.5 million on a piece of junk because it's not the right shape. It doesn't have the right things. So you need to be very thoughtful before you did this, right? Because if you go to the library and you write some crummy Python code that doesn't actually solve KDV, you wasted 5 hours of your life, but you didn't waste $1.5 million. So don't make mistakes. Questions or comments on this tank stuff, on how you build a tank for an experiment? And remember, I still have two of these up here. Yeah.
What's the best material to construct this out of? Like, what's less impactful to whatever you do with the waste?
So here are a few statements I can make. They have found that glass, not plexiglass, but actual glass, is the best thing to build their tank out of because it doesn't move and it doesn't create waves. The difficulty with glass, the glass is very fragile. So you need to have lots of metal on the outside of the glass supporting the glass. And then once you have all that metal on the outside of the glass supporting the glass, because the glass is full of water, it's very heavy, so you need a lot of metal. And then all this metal is now in the way of where you want to take your pictures or where you want to do your samples. So it's hard. But they make the tanks out of glass. Please.
How do we know we have the right dimensions of our work tank?
That's a great question. It depends on what you're trying to do. So at the beginning of this, not at the beginning of this, when we were talking about the derivation of KDV, we had this lambda and this H naught. So you have to design your tank to test the KDV equation. If you're interested in a different lambda value or a different H naught, then you need to design a different tank. But then this becomes hard, right? Because you can't just have 50 tanks because they cost too much. You want to build one that does as much as you can. Yeah. So don't make mistakes. Here's a picture of a beautiful tank. This is Vishal. This is near the new tank in Penn State. You can see the metal here that's holding the tank up. Here, there's only like 4 centimeters of water in the tank, so there's not much. This tank is got a glass wall right here. It's connected to the blue metal by that little doohickey right there and that doohickey right there. And then this white thing creates the waves, and the waves travel down the tank this way. This has no Y dimension. The Y dimension is like from that blue thing to that blue thing. It's like this direction here, but the waves don't change in that direction because the tank is only 10 inches wide, so 25 centimeters wide. So let's talk about an experiment that was not done in that tank. I don't have a tank because this tank is an old tank. Here's our figure that's not the scale, and these experiments were conducted by Joe Hammack. We have a wall here and and then a bottom here. The water is 10 centimeters deep, and then I have 5 gauges. A gauge that's 61 centimeters away from the wall, 500, 1,000, 1,500, 2,000 centimeters. We're going to create some waves over here, and we're going to see how they evolve as they go down the tank.
What are we attempting to measure with the gauges?
What we are attempting to measure with the gauges is the surface displacement of the water. So how big the waves are. We could do that with a camera, but that's not what was done in this experiment. The difficulty with using a camera, and this is like a totally interesting open problem right now, is if you take a picture of a wave and then another picture of a wave, like a video of the wave, how do you get from those photos to a discrete representation of that wave? It's a hard problem, and it's a hard problem for a couple of reasons. Number one, there's a whole bunch of metal in the way. Number two, there's background that's in the way because you've got stuff that's on the other side of your tank. And then you also have refraction, because as the light goes through the glass, as the light goes through the waves, the light gets bent. So yes, we could totally do it using cameras if we took all of those things into account. What was done in these experiments is they just put a little probe in the water and it caused a little bit of a ripple and they dealt with that. So how do we get our waves started? Well, what happens, if you look right here, the floor drops. The floor drops. What happens when the floor drops? The water drops. Yeah, so all that water drops. And then what's going to happen? This right here is 61 centimeters long. That's why this gauge is placed right there. All that water drops, and then this water here rushes in that direction, and then waves are created. And then we're going to measure how much the surface changes. 0 means the surface hasn't changed at all. A positive number means the surface has gone up. A negative number means the surface has gone down. We want to see what happens. So this is what the gauges say. The first gauge says this. Okay, the water went down, then it goes back up, and we get some oscillations. The second gauge, which is 500 centimeters away, it turns itself, it stays off for a little bit because there's nothing happening. It's 0, 0, 0, 0, 0, 0. But then once the waves get there, it says, hey, I need to turn myself on, and it starts to record what happens. It says, okay, the water goes down, then it goes up, and then it oscillates in that way. This is called like a nice front triangular wave. Just to make sure we're all on the same page, this axis right here is time. So this is what's happening at each of the gauges as a function of time. So initially, the water's doing nothing. Then, like for the first 25 seconds, the water goes down. And then at about 25 seconds, the water goes up a lot. And then it oscillates after that. Yeah.
Device to produce the stability, the wave, in order to create two symmetric waves that one move to the right or but I don't know in this construction you should have multiple waves that you are producing at the beginning because maybe there are many waves that are bouncing.
This is a great question. So when they did this experiment, they actually did 2 experiments. The first experiment, well, I don't know which order they did them in. This is one experiment that they did. And then the second one that they did is exactly the one you described. They put this in the middle. And what they found was that if this is in the middle, what happens is half the stuff goes this way and half the stuff goes that way. And it's exactly a factor of 2. So by having this, all that does is double the amplitudes of the waves that are traveling in that direction. In essence, I like to think about it as all the waves that wanted to go to the left instantly reflect and go to the right. So you get that factor of 2. Here's our epsilon and our delta for these experiments. And what did I say? Epsilon is delta squared. So 0.05 is about 0.08 squared, sort of. So let's test our models. We've got data from our tank. We've got these numerical solutions to the KdV and Woodham equations. Let's see how they do. Oh. Blue is water. Green is KdV. And these are figures. I know I showed these figures a month ago and that the green doesn't show up, but these figures I created years ago and it would take me too long to recreate the figures. What do we see? Let's look at like the 4th gauge. KdV equation says the water goes down, then it goes up, then it goes down, then so it does okay. If you look closely right here, you can see that KdV predicts this first peak reasonably well, but it's too tall. And the fact that it's too tall, someone said this, is because we don't have viscosity. KdV doesn't have viscosity, so we're going to overpredict the amplitudes. KdV is predicting that the second peak is going to get there later than it does. The third peak, it's even later. So if you look closely, you can see KdV does worse and worse as time goes on. And that's related to this long wavelength assumption we made. If you look at it over longer times, you can see, look at this. The waves totally die out, but KdV says you're going to still have a whole bunch of oscillations happening. So it does reasonable. I mean, this is pretty good. It's better than we could draw off the top of our heads, and it's reasonable. But we want to do better. We want to do better, so we're going to use the Whittem equation. We use the Whittem equation. We get some waves. We're still over predicting the amplitudes, but I get the timing right. The Whittem equation gets the timing right because it doesn't have that long wavelength restriction that the KdV equation does. So that's pretty good. And it's getting the amplitudes wrong over here in this longer time simulation, but it's reasonable. If we add viscosity, it does even better. So what did we learn? Oh, wait, what are the weaknesses of this? Blah, 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 blah. We already talked about that. This Euler instability stuff, the reason I wanted to emphasize this is because if this interests you, on Thursday, October 19th in EMAS, there's going to be a talk by Bernard de Koning, and he's the expert on Euler instabilities. And he's going to talk about how the Euler instabilities, I don't exactly know what he's going to say. He's going to talk about Euler instabilities and hopefully how they relate to the Whittem equation. So we have a whole bunch of approximations. We want to get rid of our approximations. Let's get rid of this unidirectional stuff. And when we get rid of that unidirectional stuff, it's going to turn out that we solved the Euler instability problem. So the Euler instability problem only existed because we assumed in KdV that the waves only went in one direction. So if you let waves go in both directions, the Euler instability problem goes away. How do you do this? You do what Panos did like 10 years ago, and you write this system down right here. So now, instead of having just one equation, we have two equations. So this is like twice as hard. But numerically, that just means it's half as fast. Doesn't matter. We can solve this numerically pretty easily. So 10 years ago, they came up with that system, and then 5 years ago, they came up with that system. So now we have two competing systems. These are Whittem systems for bidirectional waves. Both of these let waves go in both directions. What do you get? This is what you get. How does this picture look compared to the Whittem picture that I showed you 3 minutes ago? In this case, this guy here predicts the same as the Whittem equation does, but the Whittem equation does better than KdV. This equation does better than KdV. This is essentially identical to the KdV prediction. Why is that? Because in the experiments, the waves are only traveling in one dimension. They're only traveling in one direction. So this equation can handle waves going in that direction, but it sort of reduces to the Whittem equation when there's only waves traveling in one direction. So essentially the same. If you look at that other system, the HP system, you get basically the same results. So what did we learn? We learned that you need this Whittem stuff. You can't use KdV type equations. You want the Whittem type equations. That means you need stuff that works for short waves and long waves. And something that I ignored today is nonlinearity. Nonlinearity is important. These aren't linear experiments. So if you use a linear model, it's going to be crummy. It's not going to be very good. Okay, we're finally to the point where we're going to talk about non-horizontal seafloors, which is how does bathymetry impact the waves? That's why you came here. What does a bathymetry do? I don't know. Here's our Euler equations, blah, 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 blah. We've got this beta now that we have to deal with. What do? You do what Panos and a group of people at EMAS did, is you write this system right here down, which is the same as the system I showed you before, except now I've got this term right here. And you can do it for HP as well, that other system. You just add that term right there. And that term right there tells you how the bathymetry, how the non-flat part of the bathymetry is going to impact the waves. What does this junk mean? Let's look. So D is like a derivative. L is C inverse times A, and A and C are those integrals. Yeah, your life gets a lot more complicated if you want to do this numerically. So now your code is an order of magnitude slower than it was to solve the Whittem equation. But now we can have a non-flat seafloor. So we have code that's much more robust. Here's our experiment. This is a totally different experiment done by a total different tank. And what do we have? We have a tank that's really, really long. And this is what our bathymetry looks like. So it's, it goes up a little bit, goes up a lot, goes down like that. And then over here, someplace over here, there's a wave maker that creates the waves that travel a long distance before they get to these star places. And the star places are where we have gauges. So in this case, we have that many gauges, and we want to see how we do. This is what we observe. At the first gauge, we just see like a nice sinusoidal pattern, because that's the kind of waves they told their wave maker to make. But then by the last gauge, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, the 11th gauge, this is over the bathymetry. You can see that there's been a whole bunch of change that happens. Initially, nothing happens. The waves just sort of travel. The reason they just travel is because these first 3 gauges, well, this bathymetry is so low, it doesn't impact it. But this part right here is what's going to have the impact because it's close to the waves. You need bathymetry that's close to the waves to have a big impact. Let's zoom in on one part. Like, so this is like 2 waves for each of those gauges. If you use the HP equations, this is what you get. Blue is water, red is the HP system with bathymetry. On a scale of 1 to 10, how good did we do? You're generous. I'd say 2. I mean, okay, oh, maybe 4. Okay, yeah, sure. Over here, it does good. But as soon as you start to get over here, it does terrible. What do? You switch to the EMA system here. How do we do here? Way better, right? Way better. Those 2 equations mathematically are super similar, but their predictions are orders of magnitude different. I have no idea why. That's one of the things that I want to figure out. So what am I working on now? With Panos and Gerardo, we're studying why they're different, but really we're doing these new lab experiments. And I say we, I mean Gerardo's doing these new experiments to give me more data so I can compare them with my numerical simulations. And one of the things that's especially interesting is that his experiments don't have epsilon equal delta squared. It's like not even close. They're like a factor of 100 off. So we're going to learn something, hopefully. And then we're also studying what happens when depth is varied. Take-home messages. Whittem equations are good. Bidirectionality, good. If you have bathymetry, then sometimes this Whittem stuff works, but you have to choose the right Whittem stuff. And we don't understand why there's that difference yet. Here's some references, thank you. If you're interested in the KdV equation and the Whittem equation, this red book right here is a super good book that I highly recommend. Thank you all. Take any questions, and I still have a candy bar. Questions, please. Oh, yeah. What was the lie? Does anyone know what the lie is? For those of you who came late, I told everyone that I was going to say that there's one lie. And I'd give you a candy bar if you got the lie. So the lie is what?
There is no lie.
There is no lie. Oh, that was my lie. Yeah. So I put that statement in there because it's fun, right? Because you're going to win a candy bar. And it also covers me in case I do make a mistake, because then I can say I planned it. Yes, please.
Do you think that maybe more control, you have more control in the measure to measure the pressure in the bottom instead the amplitude of the wave?
This is good. That's another great experimental question. When they did these experiments, they measured the amplitude of the waves. Diane Henderson now she's modifying one of her tanks and she's putting pressure sensors on the bottom of her tank so she can do exactly this test. And I can't say more than that because that's all I know. Yeah, so people are very interested in that question because the pressure sensor at the bottom of the tank doesn't impact the sea, or has a very, very minuscule impact on the waves on the surface. Please.
How many orders of magnitude does it complicate to add
I don't know the answer to that question. So for those of you he just asked, how many orders of magnitude does it increase the problem to have a time-dependent bathymetry? Because remember at the beginning of the talk, I said that the bathymetry is fixed. So your bathymetry looks like this and it doesn't change in time. If it changes in time, I know how to change the Euler equations, but the work that Panos did only works for time-independent bathymetry. What happens if it's dependent? We don't know. That's a good question. There's your PhD thesis.
So, epsilon delta are functions of the thank you. They're functions epsilon and delta of the depth of the water and the length of the wave. So when the wave goes through a extreme bathymetry such as that one, epsilon and delta change spatially, and if they do, does the epsilon equal delta squared? Is that preserved along the path?
That's a great question. And the answer is no. What do? I measure epsilon and delta over here. And I say, those are my epsilons and deltas.
Okay.
And then I just deal with what I get. Because you're right. Once I change H naught, once I change my depth, I've changed my epsilon and I've changed my delta. Yeah. So my approximation is they stay constant, which they totally do not, especially here when I've got a big peak.
Okay. Thank you.
Did you see the creation of vortices in the right part of the bomb?
So I don't know Dingemans, so I don't know the answer to that question. I just have his data. In Diane's experiments, which had a flat bottom, they never observed vorticity. My guess is that vorticity was involved in this experiment. However, I assumed that there was no vorticity at the beginning of the day. So to come up with these models that we talked about today, I assumed that there's no vorticity. So hopefully the vorticity, if there was any observed, it was small. But I can't say. Yeah, that's great. Maybe there is vorticity, but maybe it doesn't impact too greatly the surface elevation.
Some vorticity can be produced, although he has a different experiment.
Yeah, that'll be interesting to say. Well, great. Thank you all for coming. I'll hang out here. If you have any last minute questions, have a great day.
Pues parece que ya terminamos oficialmente, no hubo unas palabras finales ni nada. Muchas gracias, ya voy a empezar a recoger aquí el equipo.
Sí, gracias, Álvaro. Listo.
Sí, casi no los oigo porque hay un poco de ruido aquí, pero sí entendí que ya acabamos, ¿verdad? Ya me desconecto.
Sí, ya acabamos. Gracias.
Órale, gracias, sí.
Bye.